Yeah. This distance, okay? Okay, so yeah, I'm going to talk about some simulation results and the mass dependence, possible mass dependence of galaxy rotation curve shapes, for example, and hence dark matter profiles. If I can get a start. Thinking about it. Okay, great. Yep. So I'm now in the Canary Islands, if you notice there. And this is work with a grad student of mine, Isabel in Autónoma in Madrid, and Ariana and the Niehaus crowd, Aaron and Andrea, and some help with some observers as well, actually. So I'm going to quickly run through simulations just for an outline. Okay, of course, the nice thing about cosmological simulations is that we have very good initial conditions, okay? And this is very helpful because many modeling situations, initial conditions can cause a lot of problem. The first thing you can just model is gravity, of course. So you can put in your initial conditions from cosmological simulation and just run gravity, and everyone knows what the outcome is. And I've just given this to shout out to Anatoly so he doesn't bite my head off later on in the talk. Sorry? Yep, yep, okay. And then for these high resolution simulations, we just pick a halo that we like and zoom in, go back and see where things started from and re-simulate that halo and get a galaxy. So we can do things at high resolution. Then we start to include not only gravity, but gas dynamics, all right? And things like UV background, gas cooling, star formation in various ways, and some energy feedback, all right? And in many senses, our model that we've been using for the last long time is relatively simple, okay? It's not as sophisticated as some of the new models that are coming forward today. We're increasing the sophistication, of course, everyone is as we go, but they've given us a lot of insight into galaxy formation, which is what they're designed to do, okay? So I'm going to just look at some of the insights we've gained from using these models. So one of the big breakthroughs that we first made, right, was, and I was thinking about this, I came here probably first 10 years ago, I think, and what people were able to manage to do with their simulations was get the Tully Fisher relation. And this was a big thing, everyone was trying to get the Tully Fisher relation, and we were here showing that we could get the Tully Fisher relation, and Aaron Dutton pointed out, yeah, but your sizes are completely wrong, right? Because it was much harder to self-consistently get all the scaling relations. And so simulations since then have really been able to do this, okay? Match a whole bunch of scaling relations with the current simulations that we've got. And this is probably the first paper that really was able to do that, as far as I'm concerned. The other thing that came out of these simulations is that when we started matching these scaling relations, it was because we were increasing the amount of feedback we were putting in. And the increased feedback meant that we started polluting the CGM with metals. Okay, so this was an outcome of trying to match the scaling relations. It wasn't what we were trying to achieve at the time. So it's really great to see that people are starting to really use this CGM to constrain simulations and do much more sophisticated work on this. So that's really nice. So this was a failed model in terms of scaling relations, and this was a good model in terms of scaling relations. We start polluting the CGM. Now, the other thing that came out is when we started matching these scaling relations, again, we weren't trying to do this, but we started getting rotation curves with much nicer shapes. And of course, the problem was too much gas had been cooling to the center, forming a whole bunch of mass, making these huge inner peaks in the rotation curve shapes. And we started getting these rotation curve shapes that made sense. And one of the outcomes of this was these outflows were actually changing our dark matter profile in the inner region from the simulations. And we were getting these flatter inner dark matter profiles. So instead of getting these adiabatic contraction, we were getting in low mass halos, we were getting these expansion of the dark matter halo. Again, it wasn't put into the simulations, it's just something that came out when we started matching. And there's a whole bunch of papers, of course, that have been written about this. And it's explained well in this Andrew Ponson review paper. The mechanisms that allow expansion due to outflows of gas, large-scale outflows. So what I'm going to talk about more is that the degree of this flattening of the halos has a mass dependence, right? And so this really was first shown in Ariana's plot, and she's plotted it as M star over M halo, okay, versus, and this is the inner slope. So this is the inner slope alpha, okay, measured at some small radius, and this is M star over M halo, and you can see NFW is basically -1. So this is an NFW for the very lowest mass galaxies, or the lowest mass, the lowest ratio of M star to M halo. And over here, we've got NFW again, and this is a round Milky Way mass. And in the middle, we get this mass-dependent inner slope. So the size of the core, or the amount that you're affecting the dark matter halo in the inner regions, depends on your galaxy mass. Okay. And in this later paper, we showed that you can just do a back of the envelope calculation and just compare the amount of energy that it takes to expand a dark matter halo and create a core, and compare that to the amount of energy that exists in the inner region of stars. So you just take out the amount of energy being released by stars in the inner region, in supernovae, and compare that to the amount of energy that it takes to expand a dark matter halo. When you do that, you also get this mass dependence, right? So it's not just coming from the simulations, you can show it in a really simple analytic model. So if you're going to expand the halo, you expect a mass dependence, and that's sort of the main point of this talk. And this is some newer simulations. It's all the Niehaus galaxies, and this is from James's review paper that's just out. All the Niehaus simulations are in green, and the fire simulations in red, and they're getting a similar region where the core formation is the most efficient, okay? And it's around here, which is M star over M halo at around -2. So one of the interesting things that we started to look at, and that comes out of this, is that you get a change from profiles being steep and then becoming flatter, then they hit a flatness peak, and then they change again to becoming steeper. And this will have effects on populations of galaxies and what you're observing in populations of galaxies. So this is, for example, the luminosity function, and these sort of effects these dark matter profiles have an effect on the luminosity function, the velocity function, sorry, because you're changing the velocity in the inner region of the galaxies depending on how big your core is. So we get this characteristic bend, and also in this velocity versus M star, basically the Tully Fisher relation, you get a flattening at the very low masses of the Tully Fisher relation. Okay, so you're getting the very lowest mass galaxies have very similar velocity dispersions, basically, which is what's observed. So this could come from this effect. So what we did next was go to this, look at the profile of these dark matter halos in the simulations, and we start with basically a double power law profile, okay? Now, the NFW profile is a double power law profile. So this here is an NFW profile if you put 1, 3, 1 for gamma, beta, and alpha, all right? So this is just an NFW-like profile. It's a double power law profile. The sharpness of transition is alpha, beta and gamma are the inner and outer slope, okay? And this is what we do. We mimic the same double power law profile, but now we're parameterizing each of these parameters, beta, gamma, and alpha, as a function of M star over M halo, as taken from the simulations. Okay? So basically, we fit dark matter profiles to our simulations using a really simple parameterization. So this is basically an NFW profile-like profile, but it has a mass dependence built in and it has the same number of free parameters. Because once you fix M star, you can do abundance matching, you've got M halo, and you're away, basically. So what you can then go and do is look at galaxy rotation curves, observe galaxy rotation curves, and use this profile to fit the rotation curves and compare that, for example, to an NFW fit to the galaxy rotation curves. And this is what we did with some observers, and it was led by Harley Katz at Cambridge, I think Martin's student. And what he showed was, okay, so here's a massive galaxy fit with an NFW profile and fit with one of these mass-dependent density profiles, okay? And basically, a galaxy similar in mass in the Milky Way, it's basically the same because the dependence with stellar mass means that they're basically the same, an NFW profile at the Milky Way mass. But at low mass galaxies, you can see that this mass-dependent profile fits much better. Okay? So you can fit chord galaxy rotation curves much better using this mass-dependent density profile than with an NFW profile. But that's not the only thing you can do, right? Because once you do a fit, you actually are deriving a halo mass. So you're fitting the profile and you can then derive a halo mass from that fit that you get. So you can then test that derived halo mass in the M star M halo relation for an NFW profile and DC14 profile using a whole bunch of galaxies from the SPARC dataset. And you can see that the DC14, this expanded halo, this mass-dependent halo, does a much better job of recovering the expected halo mass of all these observed galaxies. And just to show it's not a complete fluke, another group have done a similar process using another bunch of galaxies and got a similar encouraging result using this profile. The other way you can look at this mass dependence of rotation curve shapes is by looking at the velocity, rotational velocity at 2 kiloparsecs versus the rotation velocity at the maximum of the rotation velocity of each galaxy. So this was done by Kyle Oman, all right, using Eagle simulations, or these are Eagle simulations. This is just a lambda CDM, and these are observations. We found the observations have a much larger spread and dispersion in their V2 kiloparsecs over V max, all right? Eagle simulations basically just follow the LCDM prediction. So we looked at these in the Niehaus simulations, and because of this expansion in a certain mass range, we get a very similar, and we compared again to SPARC observational data set, we get a very similar shape in this V2 kiloparsecs versus V max, or V at the final point. One other interesting thing that came out of this, there's a few things that we don't match. Of course, there's a few galaxies that we don't match. And it was interesting that there's an overrepresentation of starburst galaxies in those galaxies that we don't reproduce. In fact, a lot of these are actually steeper than an NFW. So this might be something in that. And I just wanted to mention a couple more things that came out. This is a mass acceleration relation that our simulations were able to reproduce quite well. My student's paper coming out a couple of years, last year. Okay, so we can sort of mimic MOND once we start matching scaling relations using these simulations. The other thing that I was going to show Susan is this plot from Van Dockum. I made this a year ago or so. It was just interesting that we were predicting how thick disk formed back in 2004 from some of these simulations, all right? And this is in the literature, so these plots are coming from a 2004, 2005 paper, and the evolution looks pretty good. It wasn't a bad prediction, I think, compared to what Van Dockum's finding here. And again, we've done some other thick disk papers here, looking at how disks settle, how they first form, and I think it's our prediction for thick disk formation is looking quite good in terms of what the observers are now finding. I thought I'd just throw that in at the end. So my conclusions are, baryons are dynamically important in the inner regions of galaxies. Okay, baryons can affect the dark matter distribution, and a mass-dependent dark matter density profile works pretty well in fitting observed density profiles. And I just note that these statements could equally refer to adiabatic contraction, right? So it's nice to mention that while we're here. But in this case, it's applying to lower mass halos, and it's applying to, the statements are applying to halo expansion rather than contraction. And I'd also like to refer you to Aaron Dutton's work and Avishai's work looking at more detail of the theory and the analytics of how this expansion works and what it means for modeling galaxy formation.
Great talk. Questions? So I have, yeah.
Will you compare the observation, the rotation curve? Will you take into account the circular motion? The pressure support makes
We're doing that, yeah, we're doing that at present as well, yeah. Yeah, that one, it was just, that one was just the circular velocity, yeah. Well, the observers say that they take those into account though. So these are adjusted rotation curves from the observers, and they claim that they take into account the non-circular motions when they make the rotation curves. So you don't want to do it twice, but whether you believe them or not is up to you. Yeah.
Any other questions?
Actually, I have a quick question. So, I think you made a very valid point, and you've sort of been out in front of a lot of these problems for a couple of years, 10 years really. What worries you now? Are there, as you're trying to reproduce observations, are there things that worry you, or do you feel pretty good about galaxy dynamics, scaling relations, all that stuff?
There's a lot of work to do, and I think I hope we're at the point where different groups are starting to, model and get results that match scaling relations and things. So I hope we're at the point where we can now start finding the differences between the baryon cycle in those different groups, right? Mm-hmm. And see which one matches the CGM, or which things like I was talking to Daniel about this week. So his model has slightly different, I think, ratio between radiation feedback and thermal feedback. So it's less bursty, for example, I think. So can we really break that degeneracy and see which one fits better? Oh, that's where I think we're going. Yeah.